make sure I pronounce his name right. Armin Ronacher, is that right? Ronacher, Armin Ronacher, and his talk is about code generation in Python, dismantling Jinja. So please give him a big round of applause.
Hello, everybody. Welcome to Code Generation in Python, Dismantling Jinja. My name is Armin Ronacher. I'm the developer behind the Jinja templating engine. And this is a recap of basically changes in how code generation can be done in Python since version 2.3 now to Python 3.0, because there are a bunch of changes over the last couple of years. And Jinja 2 originally started out as an engine that supported Python 2.3. And it still supports 2.4, but there are a bunch of developments that make code generation more interesting. And then, obviously, why would you do code generation in the first place? For the what's called discuss mini site, there is a short link, bit.ly/code generation, and then you can drop various feedback in there if you want to do so. All right, so why would you do code generation? Isn't code generation really evil? And the question here is, why would code generation be actually evil? And many people say the problem with code generation or evaluating code is that it's a security problem, and that it's actually really bad for performance. But I would argue that none of these cases are true if you do proper code generation in Python. The first thing is that security-wise, code generation in Python is actually pretty secure. And the reason for this is that a lot of the built-in functions, the built-in literals in Python have a string representation that can be evaluated directly into Python code again. So you can call wrapper on any of the built-in types, and you get a representation of that object back that would evaluate to the proper object again. And the other argument, security-wise, would be that you can pollute your namespace by evaluating random code, so it could change local variables. And Python has excellent support for evaluating code in a different namespace, so this could be mitigated as well. When it comes to performance, the only alternative to code generation in Python is actually writing an interpreter on top of Python, which is not really helping it. And you have code that creates code that other code runs, which sounds really slow, but it's a lot faster than having code that code interprets on top of the Python virtual machine. All right, so why do we do it? Because there are no suitable alternatives. So use responsibly. Here is a quick introduction of how evaluating code in Python works if you do it right. So eval 101. The first thing is you compile an arbitrary string into a code object. And there are 3 arguments for the built-in compile function. The first one is the code you want to compile. On Python 2, that is typically a byte string. On Python 3, it is a Unicode string. The second argument is the file name that corresponds to this piece of code. In this case, Python recommends that if it's not coming from an actual file, you put these brackets around the string. And the third argument basically tells the compiler what the context of this piece of code is. It could be exec, in which case it contains any statements. It could be eval, in which case it can only be an expression. And there's a third type called single, which is used by the interactive Python shell, where the last expression in a list of statements can actually be printed to stand it out. And what you get back is a code object. And this code object basically contains all the information that the Python interpreter needs to evaluate this code. If you want to evaluate it, in Python 2, you would create, if you do it properly, you create a dictionary as the namespace. And then you exec code in namespace. This is a syntax not everybody knows. In Python 3, the exec statement is now a function. You would do exec code, comma, namespace, and then parenthesis closed. And the code that is executed is then executed in the context of this dictionary only. So here we have a equals 1 plus 2. And if we evaluate this in the namespace, there is a key 1, a key a, which is the value 3. So this is what was always possible with Python, starting from 2.3, which is basically how Jinja works internally. When you have Python 2.6 or later, there is a better way to do this. You could create an AST object. And there are two ways to do that. The first one is you can take a string and parse it into an AST tree. AST is short for abstract syntax tree. And you basically use ast.parse, give it a string you want to parse, and then you get back a node. And this node can then be, again, compiled into bytecode. So what's the purpose of this node? You can create it yourself, or you can modify it. Basically, all the syntax rules that Python contains of are compiled into these nodes, into a tree of these nodes. And the whole expression a equals 1 plus 2 can also be written as an AST module, which takes one node, which is an assignment. And in this assignment, we assign to the variable a. And every time we use a name or anything that can be used for reading and writing, we also have to notify it if it's used for storing or for loading. In this case, we store into a, and then the binary expression 1 plus 2. The last thing that is necessary before we can actually compile this is we need to specify line numbers and columns on every single node. And there is a handy function called fix missing locations, which will automatically add the missing information. In this case, it will always add line 1 to every single expression. But if we would have line numbers at least on the assignment node, it would just propagate the line number of the assignment nodes to all inner nodes. So if you would assign the line number 2, the name and the binary operators and the number would also be stored in line 2. And then we can compile it and execute it again. So this is the basic summary of how this works. You don't pass strings directly to eval. You compile them first. The reason for that is that you can actually keep the code object around. So you have the full advantage of not having to reparse and reevaluate the whole thing again. All you have to do is you have to keep this code object around, and the Python interpreter will then use the instructions on this code object to execute the code. And this means you have an explicit compilation to bytecode. And then you can execute it in explicit namespaces, and you avoid the problem of polluting your namespace. All right, so if we look at how Jinja internally works, there's a very basic architecture. Jinja, as I mentioned earlier, exists since Python 2.4, so it's actually quite old in how the code base works internally. But there was actually a first version of Jinja before that, which had an even even simpler compilation model. We'll quickly get to the difference between Jinja 1 and Jinja 2 later. The important part is that Jinja as a templating engine generates Python code. And it has mostly Python semantics, so it's mostly one-to-one mapping, but there are some differences. For instance, if you use a variable that doesn't exist in Python, you get a name error. In Jinja, you get an undefined object, which then allows you to print it still without giving you an error, but as soon as you do anything else with it, it errors out. And it has different scoping rules. So quick show of hands, how many of you are using Django as a templating engine? All right, and how many are using Jinja? That is quite impressive. So Jinja and Django are having C-inspired scoping rules, which basically means that if you start a loop and you modify the context within the loop, like assigning to a variable, outside of that loop, that variable will still be on the old value. So you cannot actually modify your context. And you have to map this to Python semantics, which is tricky. The way this works in Jinja is basically you have a lexer, which takes a string and then creates little tokens from that string. These tokens are then passed to parser, which then creates this tree of nodes, which then has a small analyzer which tries to figure out how variables flow through this whole program. Then it generates code, which it does by creating Python source, which it then compiles to bytecode, which it then evaluates on the runtime. And only the blue part is actually what is necessary to run the template. Everything else can be cached. So you can write your bytecode to the file system if you want to, then you avoid the whole overhead of the machinery. All right, so the complexities are basically you have different scoping rules, so they have to be mapped properly to the generated code. And the biggest problem I had with Jinja when I created this was WSGI is generator-based. So if you have a response from your view in Django or in any other framework, you can either create one huge string and pass it to the browser, or you can return a generator which creates smaller pieces of template code. So if you would want to have like a gigabyte large CSV file, and you would want to generate that, the simplest way is you write it into a string, and then you have a wasted 1 gigabyte of memory usage, and 4 gigabytes even if you use Unicode strings. And in order to actually create the generator, the whole Jinja infrastructure internally has to be generator aware, because we cannot convert a function call into an yield event on the generator without using greenlets. The other problem is that Jinja uses actual code generation, so it creates Python lines of code, which means the line numbers in the Jinja generated code do not map to the line numbers in your source template. And in order to get around this, there is an interesting hack within Jinja that remaps the line numbers on traceback objects. And the last big complexity that goes into Jinja is that it can actually run untrusted template code. And as we know, Python cannot be really sandboxed, so it has to restrict the language it implements in ways that you can actually sandbox it properly. All right, so this is how a Django or Jinja template basically looks like. You have the beginning of a list, then you iterate over all the items in a sequence, you print each and every item, and you close the list again. The basic behavior for this is you print this, and what happens between the iterations is that you push the scope. So the item is actually not exactly true, because the item should be in the scope. So if you iterate over a list of items and you assign to a variable name item, this will also be available in Python after the loop, which you typically don't want to have in a template, because it makes it for interesting debugging situations where you can actually, by accident, overwrite things that shouldn't be overwritten. So actually, each item should be after push the scope, but it's really hard to show this way. And Jinja and Django are also applying automatic escaping if you want. So in this case, we would want to automatic escape the item if it is necessary. So the simple implementation, which is how Jinja 1 worked, is you call a bunch of functions for each and every item. And instead of using local variables, you use a context object, which is very close to a dictionary. And every operation on the context is performed through this object. So for each temporary variable in this in the sequence variable in the context, you assign this to a temporary, then push the scope, and then assign the temporary to the new scope in your context. Then you can access it as you would normally, and on context pop, the item disappears. And this is actually really, really slow. If you compile this down, it's about as slow as Django templates are by themselves. You don't really gain anything in terms of performance. So the actual implementation in Jinja 2 looks like this. It assigns, at first, it resolves the sequence variable and assigns it to a local variable. Then it writes it. This would actually be a yield statement. And for each item in the sequence, it does the auto-escaping and errors out, bails out. Which is interesting, because this is actually, if you look at it, not according to the Jinja semantics. So there is no magic scoping happening. So how does this work? All right, so this is basic introduction into how the compilation works. And I do not claim that I understand compilation, because the whole Jinja engine as it exists currently, I didn't have any IT background or computer science background. So a lot of this is probably not how it's done in the book. All right, so the art of code generation, there are basically two levels. There is low and there is high level. If you would generate low-level code in Python, you would generate actual bytecode instructions. So if you assign 1 plus 2 to A, you would load the constant 1 and then load the constant 2. Then you would invoke the binary add operator, and then you store it to the variable A. The higher level would be you use AST nodes or write directly to source code. And the AST generation was introduced after Jinja was created. There was an alternative module which had an unoptimizing compiler, which was not supported on a bunch of platforms, including Google App Engine. So the building blocks are bytecode, which is the very low level, the abstract syntax trees, and the source code. So what are the problems with bytecode? The biggest one is it's undocumented, and it doesn't work on certain environments such as Google App Engine. And this is hugely implementation specific. The biggest problem there is that the instructions actually change from one version to another of Python. So it's not that it's different between PyPy and CPython, or Python and CPython, that is actually different between CPython 2.4 and CPython 2.5. So the bytecode generation needs a lot of maintenance if you want to do that. The nice aspect of bytecode generation is that you could actually map all the Jinja semantics onto the virtual machine of Python without having to do any weird hacks. The AST one is more limited. You're basically limited to this syntax of Python. There are some differences. You can actually have a local variable called class, for instance, and it's easier to debug. And you can, like with bytecode, you could point the error directly to the correct line number. And as of Python 2.7, you can actually not segfault the interpreter with the AST, which is also good. Because you can segfault the interpreter if you use wrong bytecode instructions. There are no, unless it was changed, there were no real guards against this. The source generation works always. It's very limited and has the problem that the line numbers point to the wrong directions. And Jinja gets around this whole line number pointing to the wrong line by basically taking your traceback object, and then it uses C types to change the line numbers on the traceback object, which works, which is quite interesting, but it's not really that nice. And I wouldn't recommend doing that. Now that there are AST nodes, they're a lot better to deal with the problem. All right, so the basic idea why Jinja is actually fast, Jinja 2 is fast compared to Jinja 1 or Django templates or many other solutions, is that it's operating on the fast aspects of the Python virtual machine. If you take this code, this is faster. It's not that fast, but it's faster than this code. And the difference is basically that this code is operating on a global scope, and this code is operating on a local scope. So why is the one faster than the other? The slower code looks like this, which you can probably not really read, but what's important there is that it uses a function, bytecode instruction called load name, which does a dictionary lookup, and the faster one looks up the variable by an index. And so Python has two, so the difference is basically these couple of instructions. And basically, every variable in a local scope is indexed by a number, not by name. And you can see this in action by assigning to a local variable called A. Then you get the local scope by calling locals, and you try to modify it. And if you return A, it's actually still the old value, because the local dictionary is actually never used. In a couple of situations, Python 2, the local dictionary can be used. Mainly if you use the exec statement in a function and you don't supply a dictionary. But I think in Python 3 it's always used. So the dictionary is a lie and it doesn't work. And this is important because this way the semantics of Jinja can actually be mapped to the fast execution environment. So remember, the basic semantics are the same as before. You push the scope, you pop the scope. But obviously that's not how Python works, so how do we make it work? The solution is this one step in the Jinja compiler which does the tracking of identifiers. So for every identifier, we know how it flows through the code. And here's the big difference between Jinja 2 and Django, and why I wasn't able to make Django as fast as Jinja, is that the context in Jinja 2 is a data source, and the context in Django is a data store. And basically, Jinja doesn't allow you to modify the context in any way, shape, or form once it's in the runtime, similar to how you cannot modify the local scope in a Python function by changing the dictionary. If you take this source, so for each item in the sequence you include another template, the code that is generated looks roughly like this. you get the other template, and for every event in that other template, you return this event again. And the event means a string of evaluated template code. And here you can see the context is passed, which was the original context, plus all the modifications on the local scope. In this case, the extra item is also passed to the include. So what happens in the include stays in the include. You cannot change any variable in the include and expect it to work outside of the included template. I couldn't do that, because I would have to also know in advance at compilation time which modifications happen in the included template. As such, it's entirely impossible in Jinja, even if we would try to make it possible, to have a function that modifies the context. That just doesn't work. All right, so here's some practical examples how this works. This is the very basic. For each item in a sequence, you print the item. And this is what the code looks like when it's generated. It looks up it knows that the code needs the sequence variable, so it looks it up. And then it yields the first part of the template, then assigns missing to L item. I get to this in a moment. And then for each item in the sequence, it yields a string with the escaped item value. The reason why it assigns missing to L item is basically if you get a traceback, some debuggers allow you to inspect which local variables exist. And this way, I can easily find out which variables are actually set to missing and which are not. For Jinja, it wouldn't be necessary, because Jinja knows that after the loop, item is actually not in use. If you take this loop, for instance, here we are using the special loop variable or for loop variable in Django, which lets us print the index. And if you go back, you see there is no special counter or anything. But we want to see in which iteration of the code we are. The way it works is Jinja sees, OK, these special loop variables exist, so we need to generate more complex code. In this case, it will wrap all the execution in this loop context object. And then we have access to the loop context, which gives us the current iteration, the number of items that are in the sequence we're iterating over, and so forth. This is the more complex example. This is the same as before. But in addition, we have an item printed after the loop. And this is not the same item as in the loop. So in this situation, we would pass item is 42 to the template and a sequence of 3 items. And after the iteration, we want to get 42 as a value. And here, the compiler has to actually load it knows the item will be used later on, so it resolves it from the context. Then it assigns the item to a temporary, loops over the whole loop body again, and then afterwards reassigns item to the temporary and prints it. If we want to look how extending templates in Jinja works, it's very simple. In fact, the root function, which is the one that's always called if you evaluate the template, basically looks for the parent's environment, gets all of the blocks in there, and for each and every block, it appends the current blocks in addition, and then calls the parent template. And each block is basically just a function that points to a dictionary. The if zero yield none is inserted by the compiler for simplicity reasons. It basically forces a function to become a generator. This is showing up in more places, but I forgot to delete this here. It's by if zero yield none, it's basically removed that compilation in the Python interpreter. It doesn't do any damage. And if we just look at how a template works without inheritance, it's basically just for each and every block yielding the events, and each block is essentially a function. If we call into a super block, so one from the template above, it sees that the special variable super is used, and super is basically just an object which is created from the context object, which knows how to evaluate the parent template. All right, so here are a couple of things why Jinja works in certain ways. Why does it do manual code generation? Basically because it didn't have a chance before that. If you look at my GitHub repository, there is a new project called JSON Jinja, which attempts to have a very small version of Jinja that can be compiled into JavaScript code as well, where you have the same semantics for as long as you only pass JSON objects to the templating engine. So you can render it on the server and on the client. And this one is using AST nodes instead of actual code generation. The generators instead of buffer append is for WSGI. The problem there is if you by accident have a stop iteration as part of the template evaluation, it will just stop rendering the template. And this is a good example why you should not have in-band signaling. So stop iteration to signal the end of an iterator is actually, in this case, really painful to deal with. Why does it map a variable x to L variable x? Mostly because I have internals for that the templating engine needs for running, like the temporary variables, and this way it can just basically take the locus scope and find out what variables are actually used by the templating engine. And templatetk has a better approach. It actually supports the templatetk is the project that Jason Jinja is using. It has a better approach where it can actually encode more information into the local variables, so you can avoid having the temporaries. Just basically a couple of things, how Jinja does a couple of things. The markup object, I don't know if you know it, is basically a wrapper around the string where you can use, where the operators are all overloaded in a way that you can do as automatic escaping. So you can have a variable and append another string to it, and it will automatically escape what the string that was appended. Part of the automatic escaping in Jinja actually works at compile time. If you just print a string and the string is not safe, it will basically recognize this constant string. I can auto escape it at compile time. If it's a variable, it has to do it at runtime. And if I want to control how auto escaping works, I can use the auto escape false and disable it. And if you look closely here, it creates a new evaluation context, which is the context eval context, and sets the auto escape to false. The reason why it does this is that the runtime knows if it can actually rely on auto escaping to work or not. And here's a more complex example how this would work if the auto escape is not recognizable at compile time. All right. All the operators on the markup object are actually overloaded, so you can create a markup object from a string, and then you can pass an insecure string to the string formatting operators, and it will work. All right. This is basically an overview of how the Jinja templating engine works and how it does the code generation. There are a couple of more things that go into the whole compilation process. For instance, the undefined variables in Jinja are actually replaced by undefined objects. And you can see if I create this undefined object is always returned by the resolving of the context, so I can still convert it into an empty string. But if I attempt to do an attribute lookup on it, it will give me missing var is undefined. All right, thank you. If you have any questions, feel free to ask.
Someone has. If anybody has a question, you can please walk up to the microphone.
Great lecture first. If you had a chance to do it all over again, would you use the AST module now?
Yes, I would definitely use the AST module now, and the Jason Jinja project is using the AST module. If you actually want to use the AST module and still support the older Python versions, there is a utility library which converts any AST tree into Python code, which you can regularly compile. January slides will be online at this URL, and we are hiring.
Do we have any other questions? Yeah, I have another question.
You said that you use C types to make the line numbers line up. I'm just curious if you could kind of give an overview of how that works, if that's not possible.
It's actually a very simple process. The way it works is For every piece of code that the Jinja template engine creates, it inserts a special global variable into the namespace called __Jinja debug information something, where it has the line number mapping. So it knows what the source line number is and what the expected generated line number is. And then if I get the traceback, I walk over all the frames in the traceback. And for every one where I see the special marker in there, I create a new code object which has the correct line number, and then I monkey patch it onto the traceback object. And it works on all Python versions I tested it with. It also works on PyPy, because PyPy has a special proxy object which can be used to fake the internal traceback object. So that's actually really useful. It did, however, show up that Python had a bug on some, I don't even know what architecture was, Spark something, where the object size was not correct. And then Jinja was suddenly segfaulting on some 64-bit Spark machines. So there are some problems you can have with these kinds of monkey patches.
Thank you.
Okay, but that's all the time we have for today. We want to thank Armin for his talk, and